Hey everyone, Mrs. Hanson here once again. Doing our work in chapter 5 is turning into a more of a quantitative chapter at this point in time and to completion. So that means as we begin this lesson, please have out your calculator. You'll want to have your mole map and your stoichiometry map, all of these things that are going to be useful tools for this half of the chapter. A very, very number crunching type of chapter from this point forward. So calculators on and ready. Please don't wait till quiz day to become familiar with how to operate your calculator. Do so with me each time we work a problem. Make sure you hit your calculator keys to indeed ensure that you're hitting them in the correct sequence, leading you to correct answers. So many times I've seen students just wait until test day and then can't figure out how to enter scientific notation on their calculator. So that's my piece of advice for you as we begin with the mole and Avogadro's number. What is a mole, you might ask? In chemistry, a mole is a counting unit. A mole represents a quantity that contains Avogadro's number, 6.02 times 10 to the 23rd, anything. 6.02 times 10 to the 23rd represents the quantity mole. It is known as Avogadro's number. A mole can represent individual atoms of elements. It can represent molecules of water. It can represent molecules of large complex molecules such as vitamin C. There are certain words that represent numbers. If I say the word dozen, you think of the number 12. If I think of a word called pair, you think of 2. If I say a gross, that's a dozen, that's 144. A ream of paper contains 500 sheets. These are words that represent numbers. When I say the mole, you think of the number 6.02 times 10 to the 23rd. I can have moles of atoms, molecules, ions, pencils, anything. It's just a number, 6.02 times 10 to the 23rd. And it is a really big number because atoms are so small. This is known as Avogadro's number, named for an Italian chemist in honorarium for his work in deciding this number. Was never counted, but it was derived. This is a mole map that allows us to figure out how to convert between specific ways we measure matter and the mole. When we measure matter, and I don't care if we're in the lab or down the Meijer aisle when we're grocery shopping, we measure matter in one of 3 ways. Measure lab. We measure matter in the lab one of 3 ways. We can count, we can weigh, or we can take a volume. Each one of those measurements lead back to the unit known as the mole, the central calculation of all of chemistry, the mole. All roads lead to the mole. We can count individual representative particles. We can count atoms of elements. We can count molecules. We can count formula units. We can count ions. All of those individual building blocks of atoms, molecules, formula units, and ions. Notice that the road leading from these individual atoms can lead into the mole by using an exchange, a conversion factor known as Avogadro's number. A conversion factor is an equivalence, isn't it? We know that 1 mole is exactly the same thing as saying 6.02 times 10 to the 23rd, and I'll just use that general term particles. Notice these are individual building blocks of matter. If I want to start from the number of particles and go into the mole, I can see that I divide by Avogadro's number. If I'm at the mole and want to head out to the number of individual particles called atoms or molecules, I know that I can see to multiply by Avogadro's number. There is a pathway between counting and the mole, things that we count. Let's say I'm walking down the store at Meijer's and I put a dozen eggs in my cart. I counted to 12. I could buy a dozen donuts and I would get 12. I could buy a mole of donuts, and I would get 6.023 times 10 to the 23rd particles, or donuts in that case. There is another way we measure matter, and that's by weighing it. And notice that is a mass in grams. That's a scale. Sitting on this is I don't know, it looks like a sample of matter, maybe a lump of carbon. I don't know, it looks like a black piece of coal, so carbon atoms. How much would 1 mole of carbon weigh? We'll learn that that's the term known as molar mass. The molar mass, we'll learn, is also called the formula weight, which is really just the weight off of the periodic table. The formula weight, the weight of 1 mole of either an element or compound. For carbon, you know whose atomic mass is 12. I would have 12 grams of carbon sitting on this scale to have exactly 1 mole of carbon, which is the same as saying 6.02 times 10 to the 23rd carbon atoms. Do you know that the mole allows us to count by weighing? So if I walked to the scale and I laid out 12 grams of carbon. Now why 12? Because carbon's atomic mass is 12.011 or something very similar. I'll just round to say 12 grams. The weight off the periodic table is 12 for carbon. The mass of 1 mole matches the gram atomic mass of carbon. 1 mole is exactly 6.02 times 10 to the 23rd atoms of carbon. By weighing, I now know how many atoms I have. The mole is an exchange unit. It allows us to measure matter by counting, by weighing, or by taking a volume. But all roads lead into and out of the unit mole, the central calculation. Now I'll comment, the volume, there is a third type of measurement. When we take a volume, let's say in liters, we're measuring a gas. So this will come out in a later chapter when we study our gas laws. And just to emphasize, the 2 roads on our mole map that we will be investigating will be converting from grams to moles, or moles to particles, or any other combination of each. We will have 1-step mole problems. We could have a 1-step mole problem this direction, or we could have a 2-step mole problem, but focusing simply on weighing and counting. And later in our chapters, when we study the gas laws, we'll bring out that third map, leading north to the world of volume. All right, so all of that kind of working up to this very first sample question. How many molecules are contained in 5 moles of carbon dioxide? Let me give myself some room to clean up this page. Sounds like I'm getting emails. All right, so let's see. Let's figure out using our roadmap, and this is really the key. If you're a visual learner, this is your key to success. I'm going to say, what unit are we given and what unit do we want to know? We're given 5 moles of carbon dioxide. We want to know molecules. Now let's figure out what that means on this graph, on this roadmap. The unit I'm given is 5 moles. That puts me right here in the heartland of the mole map, right here in the center. I want to know individual molecules of carbon dioxide. My want is the individual particles. My given is the mole. And friends, you will literally trip over the conversion factor as you follow the arrows out of the mole towards the particles. Always begin by writing your number and your unit. We had 5 moles of carbon dioxide. We are going to set up a mole ratio, just a conversion factor that will cancel out the mole and bring us to Avogadro. Now look at, you see this? That's our conversion factor. We know that 6.02 times 10 to the 23rd And particles in this case will be the individual molecules of carbon dioxide, is equivalent to saying 1 mole. This is our conversion factor. And a conversion factor cancels units. We can see that the mole of CO2 will cancel and we'll have molecules of CO2. So the roadmap says given a mole, you're going to head out. And when you head out, you'd multiply by Avogadro. Now what about your key sequence here on your calculator? 5 times Avogadro's number, 6.02, and on your calculator, you use the scientific notation key, EE, or on my calculator, I have a TI-84 and it has an EE key, but it may also be an EXP. So it depends upon your calculator. So it might say EE or it might say EXP. And that's our key sequence. So let me model that using just the Google calculator here. We had 5 moles, 5, and we want to multiply that by Avogadro's number. So 6.02, and then see how I have an EXP key? The EXP raises the power of 10. So 5 times 6.02, the E is scientific notation. It means times 10 raised to the 23rd power. And on your calculator, it should say 3.01 times 10 to the 24th. That's how we read that. My goodness, I just forgot what it said. 3.01 times 10 to the 24th. And that would be a molecule of carbon dioxide. Try it on your calculator. 5 times Avogadro's number so that you're confident we have a common answer. We converted 5 moles into the number of individual carbon dioxide molecules. We multiplied by Avogadro. Here's some practices with that very skill. How many molecules are contained in each of the following moles? We are given the mole. We want the individual particles. You will literally trip over your conversion factor heading out of the mole to the individual molecules means to multiply by Avogadro. 2.5 moles of penicillin multiplied by the conversion factor, 6.02 times 10 to the 23rd molecules is the same as saying 1 mole. Those are equivalents. Therefore, I'm setting up a conversion factor. Moles cancel, and your conversion would say 2.5 times the Avogadro's number on your calculator. 2.5 times Avogadro's number. Hit it with me, please. My screen says 1.5 times 10 to the 24th molecules. Let's try another. Here we have 0.25 moles of ammonia. We would like to know how many individual molecules that is. You're at the mole, heading out. To head out, you multiply by Avogadro's number. Please set this work up in your note packs. Don't just write an answer. I want to see the work shown always. For full credit in your note pack, show your work. 0.25 times Avogadro. And this gives us an answer of 1.5 times 10 to the 23rd power of 10 there. And that's the molecules of ammonia. We're getting the hang of it. Mole times Avogadro to convert to the individual molecules. For letter C, 0.4 times Avogadro. And for letter D, it will be 55.3 times Avogadro's number. The conversion between the mole and the individual particle relies on Avogadro's number, 6.02 times 10 to the 23rd. 0.4 times Avogadro's number gives me a value of 2.4 times 10 to the 23rd molecules. 55.3 times Avogadro, and that gives me 3.33 times 10 to the 25th power molecules. Mole times Avogadro converts it into individual particles. As our mole map suggests, heading out of the mole, we use Avogadro and multiply. What if we needed to go the opposite way? Notice here, how many moles means that's what we want. We want to know the moles. And this time we're given the individual particles, the number of molecules of aspirin. So I want you to notice your pathway here is a little different, isn't it? You're given the molecules and we want to head into the mole. Heading in means we're going to divide by Avogadro. 8.62 times 10 to the 25th molecules is what we are given. We want to set up a conversion factor that cancels the molecules and brings us to the mole. Heading in means we divide. 1 mole is, whoops, I wrote mole twice. 1 mole is equivalent as saying 6.02 times 10 to the 23rd molecules of our aspirin. So on your calculator, 8.62, then your scientific notation key, 25, divided by Avogadro. And what does it say? Practice hitting that, please. 143. I'll put 2 decimals in, just as our number does, 0.19, and that's the number of moles of aspirin. Now think about what we just did in our calculator. All right, just to model it, we started with 8.26, and then I used my scientific notation key and raised that to the 25th power. I then divided it by Avogadro's number, 6.02, use your scientific notation key, 23rd power. That's how I'm finding 100. Oops, did I hit something wrong? Oh, I had a moment of dyslexia. Darn it, let me hit that again. 8.62, I think I had that backwards. And then I'll hit EXP, 25th power, divided by Avogadro's number. And now I have on my screen 143.19, and that will be moles of aspirin. The reason I'm emphasizing that is make sure you know how to calculate using your scientific notation key. And that's what you'll have on your calculator on your screen for your quiz is an online calculator, so you have to learn how to use that EXP key. So how many moles of water contained in each of the following number of molecules? If I have 6.02 times 10 to the 25th molecules, this is me starting right here. Given the number of molecules, I want to go into the mole. I trip over my conversion factor. 1 mole is the same as saying 6.02 times 10 to the 23rd molecules. So my conversion factor will have me divide by Avogadro. And what do you find when you hit that out? Whoops, that was a 25. Does your screen say 100? You're right, 100 moles of water. 3.01 times 10 to the 22 molecules divided by Avogadro. Write your work out with me. Don't go back and try to study and just see a number there without any clue of how you got it. So show the work in your notepad. Hitting that out on your calculator, solving for the number of moles, 0.05 moles. And one more. 9 times 10 to the 24th molecules. Converting to a mole means we're going to divide by Avogadro. There is an Avogadro's number of molecules in that mole. So 9EE24 divide by 6.02 EE23, and I find 14.95 moles. I'll just say 15 moles. Remember, one more time, just to emphasize, when I'm calculating out, I would start by saying 9, and then there's my times 10 to the EE key or the EXP key, and I'm going to raise that to the 24th power. That reads 9 times 10 to the 24th. I'll divide by Avogadro, 6.02 EXP 23rd, and that's my answer, 14.95. The term molar mass or formula weight is the mass of 1 mole of any element or compound. It is found by adding the atomic weights of each atom up in a formula. The term molar mass or formula weight is used as a conversion factor to exchange between mass in grams and the central unit of all, the mole. The term molar mass, the mass of 1 mole of anything. The mass of 1 mole of any compound or element is called the molar mass. Sometimes you'll hear people call it the formula weight. And it's used for a conversion factor. It's used as a conversion factor to exchange between mass in grams and the word mole. Let me emphasize by backing up a slide just to show you that when I weigh something out in grams and I'd like to know how many moles it is, you can see that the conversion factor we'll use is the term molar mass. Since every atom weighs a different amount, there is no set number like over here. So the molar mass is unique to each compound. Whereas when I'm counting, it doesn't matter what I'm counting. It's always the same number over here, always 6.02 times 10 to the 23rd. So what we're learning is that the term molar mass is our conversion factor between the world of grams and the world of moles. And that exchange relies on adding the molar mass of each compound. Let's practice learning how to calculate molar mass. Let's do our first compound, iron 2 sulfate. We have to be able to write a formula, and this is just so critical that if I can't write a formula correctly, I'll never get the correct molar mass, and therefore my math will never be correct. These are just fundamental skills that you have to keep practicing over and over, writing a formula correctly. Well, iron is the elemental symbol Fe. Iron with the Roman numeral 2 tells me it's a +2 charge. Sulfate is a polyatomic ion. The polyatomic ion chart is still provided for you, but you should become so familiar with it that they just start to sound familiar. Sulfate is a polyatomic ion that carries a -2 charge. My compound is FeSO4. The name, iron 2 sulfate. What is its molar mass? What I'm asking you is, how much would I weigh out to get 1 mole of iron 2 sulfite? That answer relies on looking up each individual element and adding up its atomic weight. Now, in our compound, there's 1 iron. Iron has a molar mass of 55.85. In the formula, there's 1 sulfur, Sulfur has a molar mass of 32.06 grams. And oxygen is 16.0, but we have 4 of them in there altogether. Find the sum of all of those atoms. I have to add 55.85 plus 32.06 plus 4 times 16, which is 64, and I get a sum of 151.91 grams. The molar mass, which is the mass of 1 mole of iron 2 sulfate, is 151.91 grams. Shall we try another? Let's write the molar mass of calcium carbonate. Calcium, right here, lives in column 2A, so I know it's a +2 charge. Carbonate, a polyatomic ion. If you don't have those memorized, please consider just really spending time with that so you would get more proficient, means speed. Calcium carbonate, CaCO3. If I can't write a correct formula, I'll never get a correct molar mass, and therefore, I'll never get my math right. Calcium has a molar mass of 40.08. Carbon has a molar mass of 12.01. Oxygen has a molar mass of 16, but there are 3 of them in the formula, so let's sum all of the atoms. 40.08 plus 12.01 plus 16 times 3, and I get 100.09 grams. One more. What is the molar mass of nicotine, the toxic addictive stimulant found in tobacco? Well, the nicotine's formula is C10H14N2. I'm going to give myself some workspace, so I'm going to erase my calcium carbonate work and give myself the space here for nicotine. Okay, carbon has a molar mass of 12.01, and there's 10 of them in the compound. Hydrogen has a molar mass of 1.01, and there's 14 of them in the compound. And nitrogen's molar mass right here is 14.01, and there's 2 of them. Let's sum all the atoms to find the mass of 1 mole of nicotine. 12.01 times 10 plus 1.01 times 14 plus 14.01 times 2. That sums to 162.26 grams. The molar mass of nicotine, the mass of 1 mole of a compound. Now, we said that that was a conversion factor that leads us from the mole to the scale, or vice versa. Molar mass is our conversion factor between the world of grams and moles. Given a gram and we want a mole, we know to divide by molar mass to head in. Given a mole and we want the grams, you can see that you will multiply to head out of the mole. That's true always. Heading out of the mole, multiply. Heading into the mole, divide. And that's the same if you're multiplying or dividing for any of the ways we measure matter. So let's try our first practice problem with our mole map. What is the mass of 0.25 moles of water? So we can see that we're given, in terms of the unit, the word mole. Our given unit is the mole. What do we want to know? Well, we want to know the mass. And the mass is this scale right here. That's the mass measured in grams. Excuse me. So Here I am at the mole, and I want to head out. You can see that you literally trip over your conversion factor. We need the molar mass of water. Well, the formula for water is H2O. Hydrogen has a molar mass of 1.01. Oops, it went away. Hydrogen, 1.01. Oxygen is 16.00. So when we add two H's and an O, we get roughly 18, don't we? 1.01 times 2, add the 16, and you get 18.02 grams as the molar mass of water, the mass of 1 mole. That's our conversion factor. So this number of moles given, using our conversion factor, the molar mass on top, the mole unit on bottom. If I weighed out 1 mole of water, it would weigh 18.02 grams. I'll carry that decimal with me. .25 times 18.02, and I find 4.505, so I'll round that to 4.51. That's fine for sig figs. 4.5, 4.51, whatever you'd like there, that's fine. And then our unit here would be grams of water. Calculate the grams in each of the following number of moles. I would recommend you pause the video and practice your own mole map problems. You're given the moles, you need to multiply by molar mass. Multiplying by molar mass takes a little time with you in your periodic table to find the element's weight. The only way to get better is to practice. Come back when you have some answers. Okay, you started back up. I hope you really paused. 0.5 moles of sodium chloride. We need the molar mass. I'll just do that down here. Na has a molar mass of 23. And just to confirm, I've got to always go back to my periodic table. 22.99. That was close. Chlorine, NaCl, so that's 35.45. So when I add 22.99 plus 35.45, the molar mass, 58.44. So that's my conversion factor. 58.44 grams is the molar mass of 1 mole of salt. So my conversion factor would take 0.5 times that molar mass, and we find an answer of 29.22 grams of sodium chloride. Next one, potassium iodide. I'm going to just take out a periodic table so I can have one handy here. Here's one for my papers. Then I don't have to keep flipping slides. So here in letter B, potassium with its molar mass of 39.1, and iodide, I, is 126.9. So I'm adding up the K plus the I. 39.1 plus 126.9, that came out to 166. That's the molar mass of potassium iodide. 2 moles of potassium iodide can convert into grams by using the conversion factor of 166 grams of potassium iodide being equivalent to 1 mole. 2 divided by the molar mass, 2 times the molar mass, and I have 332, I'm going to pause that, 332 grams. Here's letter C. We had to do C2H4. All right, C2H4. Carbon with a molar mass of 12.01, but there's two of them. Hydrogen has a molar mass of 1.01, and there's two of them. Nope, there's four of them. (12.01 times 2 plus 1.01 times 4 gives me a sum of 28.06 grams as my molar mass. And that can really be done on the calculator. Using that as my conversion factor, I know that 1 mole would have a mass of 28.06 grams for every 1 mole. So molar mass times 3.6, and what'd you find? My screen says 101.016 C2H4. And we have a letter D. We can certainly check together. Give yourself some feedback. 0.820 moles of methanol, CH4O. We're going to need its molar mass and convert over to a gram. Carbon, we said, had a molar mass of 12.01. There's one of those. Hydrogen has a molar mass of 1.01, and oxygen is 16. Let's sum those. 12.01 plus 1.01 times 4 plus 16. I get 32.05 grams. The mass of 1 mole of methanol. Moles times molar mass. And we've converted into 26.281 grams. That's 3 decimal points. So 26.281 grams. 3 sig figs, 26.3 grams. There we go. So we've been practicing converting from moles to grams or grams to moles. Let's try some other ideas. What if we start with grams and we want to go into the mole? Now notice that we're heading into the mole so we can see how it's divided by. 100 grams of aspirin. We need a conversion factor that will count the number of moles of aspirin. So notice that I have to do a little calculator work. 12.01 times 9 for the carbon, 1.01 times 8 for the hydrogen, and 16 times 4 for the oxygen. Let me sum the molar mass. Did you find it? 180.17 as our molar mass. That now needs to go on the bottom so the grams cancel. Right, we're heading in, so we know to divide. 180.17, our conversion factor. So let's start by hitting 100, and then you divide by that molar mass. 100 divided by 180.17. 0.555. And that's our number of moles of C9H8O4. Pause the video and work these ahead. I'd like you to convert grams to moles, then come back and check your work. Don't cheat yourself of the practice. You'll notice on test day, if you haven't practiced, you need to. Okay, you've come back, so let's see what we have. I'm going to do some molar mass work. Sodium, 22.99. Chlorine, 35.45. The molar mass of table salt, 22.99 plus 35.45 and I get 58.44 grams. 100 grams of sodium chloride. To convert into the mole, right? That's our target. See what we're doing here? We want to go into the mole, so I'm literally tripping over my conversion factor. I need to divide by the molar mass. Here, methane, 25.5 grams of methane, CH4, times a conversion factor, where 1 mole of methane has a molar mass of, let's see, 12.01 plus 1.01 times 4 is 16.05 grams. How about letter C? 0.250 grams of aspirin times a conversion factor that will cancel grams and bring me into the mole. Let's see, 12.01 times 9 plus 1.01 times 8 plus 16 times 4. This molar mass was 180.17. 180.17 grams. The mass of 1 mole. And one more to set up, 25 grams of water. We use our molar mass as our conversion. 1 mole of water has a molar mass of 18.02 grams. That was you adding up an 8, 2 H's and an O. Now I'm ready to just go through and hit these. 100 divided by 58.44. That's 1.71. 25.5 divided by 16.05, 1.59. 0.25 divided by 180.17, 0.00139. I'm rounding there. And 25 divided by 18.02 is 1.39. Now those were you checking your work. You didn't cheat yourself, you worked ahead, and you just checked your answers with me. How'd you do? How about two-steppers? Grams to molecules. How many molecules are contained in 325 milligrams of aspirin? I walked to the scale and I weighed out some aspirin tablets, and the scale read 325 milligrams. How many individual molecules are there? Well, notice that there is no direct pathway between grams and particles. There's no one road to lead me there, but I do see a two-step pathway. I can go into the mole and then back out to the number of particles. So I want to start at the number of grams. Now I noticed that it gave me milligrams, but I have to remember that milligrams is not what the scale should be reading in, that there's 1,000 milligrams in a gram. That molar mass must be in a gram. Times, alrighty, so that's, let me just do that, slide that over, that's 0.325 grams. That's my starting amount. So this is what I'm given, and I want to know how many molecules that is. The other thing that we need to go back maybe and just remind ourselves, we've been using aspirin a few times, C9H8O4. So let's remember its molar mass, 180.17 grams. We've worked that a few times. So Here we are down here at 0.325 grams. I've got to go into the mole and then out to Avogadro, 2 steps. So let's set that up. I have 0.325 grams. I'm going to go into the mole by using the molar mass of aspirin, C9H8O. The molar mass of aspirin we said was 180.17 grams. So that's our first conversion. That led us from mass to mole. Now here we're standing. We want to go out now to the individual particles. Heading out, we know we multiply. And when we're counting, we use Avogadro's number to represent the molecules in 1 mole. Now, here's an example. 0.325 divided by 180.17 times Avogadro, a 2-step conversion. My screen reads 1.085, let me just round, 1.09 times 10 to the 21st power molecules of C9H8O. That's our formula for aspirin. Oh no, C9H8O4. I missed that 4 there. I'll correct that just to make sure I can see that where that 180.17 came from. 180.17, just to make sure you see that I added those properly. I want to make that neater. Now, just to kind of consider what that means, that's how many molecules of C9H8O4. If I have 1.09 times 10 to the 21st molecules of that compound, you would actually have 9 times as many carbon atoms, 8 times as many individual oxygens, and 4 times the oxygens. So let's make sure that we can see that, because I know that sometimes you're asked to go even 1 step further, and I want to model what we're doing here. The compound is a large structure made of 9 carbons, 8 hydrogens, and 4 oxygens. If I were to ask to count individual particles, notice that there are 9 carbons in every 1 molecule. So I would take the answer that's on my screen right now, 1.09 times 10 raised to the 21st power times 9. And that tells me that in that compound, there's actually 9.81 times 10 to the 21st carbon atoms. And there would be 1.09 times 10 to the 21st molecules. The big compound contains 8 hydrogen atoms. In every 1 molecule. And so if I had been asked to count individual hydrogens, I would have to take my 1.09 E21 times 8 to find the total number of hydrogen atoms. And there's one more atom we could count. In this 1.09 times 10 to the 21st molecules of aspirin, there are 4 individual oxygen atoms in every 1 molecule. So counting the individual oxygens, 1.09 E21 times 4. And I've got 4.36 times 10 to the 21 oxygen atoms. So the compound itself, individual molecules, 1.09 times 10 to the 21st particles called molecules, but they're built of smaller things, aren't they? There's inside 1 molecule, it's containing 9 carbons, 8 hydrogens, and 4 oxygens. So I wanted to model that you may be even counting something smaller, such as individual atoms within a larger compound. Great work there. That was a lot of good practice. How many molecules are contained in 2 500 milligram tablets of penicillin? Well, we're given a mass and we want to know individual particles. How many molecules of penicillin? Well, 2 500 milligram tablets. 2 tablets. How many total tablet then? What's 500 plus 500? Well, that's 1,000, right? 1,000 milligrams. But I know that when I do mole map work, I need it to be in a gram. And the term milli means 1,000. So when you said 500 plus 500, because you're taking 2 tablets, that's 1,000 milligrams. And you're going to divide that by 1,000 to convert it back into a gram. So all of that talk was you're saying you're starting with 1 gram of penicillin at that scale. We need the molar mass of penicillin, and I don't know that one by heart, so we'll have to do some work. Carbon, with its molar mass of 12.01, and there's 16 of them there. Hydrogen, its molar mass, 1.01, and there's 18 of them. Nitrogen has a molar mass of 14.01. Oxygen is exactly 16, and there's 4 of them. And sulfur, with its molar mass, 32.06, and there's just 1 of those. So let's sum the molar mass. 12.01 times 16 plus 1.01 times 18 plus 14.01 times 2 plus 16 times 4 plus 32.06. So that found 334.42 grams. That's our molar mass. So, given a gram, we want to go into the mole, divide by molar mass, head out to the particles, multiply by Avogadro. We start with 1 gram of C16H18N2O4S times. Heading into the mole, we're going to use the molar mass we just calculated, 334.42 grams. Now I'm standing at the heartland of my mole map. I'm right in the center of the mole, and I want to head out to the individual particles. Whoops, a moment of dyslexia. 6.02 times 10 to the 23rd. And that will give us the molecules of penicillin. 1 divided by 334.42 times 6.02 EE23. And my screen reads 1.80 times 10 to the 21st power. That's molecules of this big old compound that contains 16 carbons, 18 hydrogens, 2 nitrogens, 4 oxygens, and a sulfur. That's a big compound, but that's how many molecules of that big compound you have. If you had to count individual atoms, you would then look at the subscripts to do so. You did great work. With that part of the lesson, we really have done just exploration with the mole concept. We took an hour to do that section to really practice our mole map. When you come back for the next video, we'll be on section 7, and we're going to take the mole map and apply it to a balanced chemical equation. Our goal is to be able to read a balanced equation as if it were a recipe card. Come back when ready.